When students first learn chemical equations, balancing them and predicting products already feels like a huge accomplishment. But then there is another challenge that causes a lot of confusion in General Chemistry 1, figuring out the correct states of matter. Have you ever balanced an equation perfectly and still gotten the problem wrong because you wrote the wrong state? That happens all the time in chemistry. States of matter are not just labels your professor adds for decoration. They tell us what is physically happening during the reaction. They tell us whether a substance stays dissolved in water, forms a precipitate, becomes a gas, or remains a liquid. And later in chemistry, states of matter become extremely important for net ionic equations, precipitation reactions, and stoichiometry problems. The good news is that figuring out states of matter is actually very systematic. Once you learn a few rules, you can predict the state of matter for almost any reactant or product you see in general chemistry. The 4 common states of matter we use in chemical equations are solid, written as S, liquid, written as L, gas, written as G, and aqueous, written as AQ. Aqueous means the substance is dissolved in water as ions. In this video, we are going to learn a step-by-step system for determining the correct state of matter for compounds and elements in chemical equations. The first question we should ask is this: is the substance an element by itself, or is it a compound? Let's start with elements. When elements appear alone in a chemical equation, they exist in their natural form. Most metals are solids at room temperature. For example, sodium would be written as Na solid, and iron would be written as Fe solid. One important exception is mercury. Mercury is a liquid, so it would be written as Hg liquid. Next, we have a special group of elements called the diatomic elements. These elements naturally exist in pairs. A common way to memorize them is the phrase Brinkelhoff. These elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When written alone in an equation, they must appear as pairs. For example, hydrogen becomes H2 gas, oxygen becomes O2 gas, nitrogen becomes N2 gas, chlorine becomes Cl2 gas. Bromine is unique because it is a liquid, written as Br2 liquid. Iodine is a solid, written as I2 solid. And fluorine is a gas, written as F2 gas. Some other important elemental forms are phosphorus, sulfur, and silicon. Phosphorus naturally exists as P4 solid. Sulfur naturally exists as S8 solid. Silicon exists as Si solid. Now you might be wondering how we are supposed to know the natural form and state of matter for all the other elements. A very useful tool in general chemistry is the thermodynamic table found in the back of most chemistry textbooks. These tables list values such as delta HF, the enthalpy of formation, and delta GF, the Gibbs free energy of formation. Any element in its natural standard state will have a delta HF value of 0 and a delta GF value of 0. That tells us the correct form and state of matter for how the element naturally exists by itself. For example, phosphorus appears as P4 solid, sulfur appears as S8 solid, and silicon appears as Si solid in their natural standard states. So whenever you are unsure how an element exists alone in a chemical equation, the thermodynamic table can help you determine the correct form and state of matter. Now let's move on to compounds. For compounds, the first thing we should determine is whether the compound is ionic or molecular. Ionic compounds usually contain a metal bonded to a nonmetal, or they contain a polyatomic ion. For example, sodium chloride, NaCl, is ionic because sodium is a metal and chlorine is a nonmetal. Calcium carbonate, CaCO3, is also ionic because carbonate is a polyatomic ion. To determine the state of matter for ionic compounds, we use the solubility rules. The solubility rules are one of the most important topics in general chemistry. The idea is simple. If the ionic compound is soluble in water, we write aqueous. If the ionic compound is insoluble in water, we write solid. An insoluble solid formed during a reaction is called a precipitate. Now let's go through the most important solubility rules students should memorize. First, compounds containing group 1 metals are always soluble. That means sodium, potassium, and lithium compounds are almost always aqueous. For example, sodium chloride would be written as NaCl aqueous. Next, ammonium compounds are always soluble. Nitrates are also always soluble. So if you see NO3 negative, the compound will almost always be aqueous. Acetates are also generally soluble. All chlorides, bromides, and iodides are soluble unless they are paired with silver, lead, or mercury 1. Now let's discuss some commonly insoluble ions. Carbonates and phosphates are insoluble unless they are paired with group 1 metals or ammonium. Hydroxides are insoluble unless they are paired with group 1 metals, ammonium, strontium, or barium. Sulfides are insoluble unless they are paired with group 1 metals, group 2 metals, or ammonium. For example, calcium carbonate is insoluble, so we write CaCO3 solid. Silver chloride is another famous insoluble compound, so it is written as AgCl solid. Let's look at an example reaction. Silver nitrate aqueous reacts with sodium chloride aqueous to produce silver chloride solid and sodium nitrate aqueous. Why? Silver nitrate is aqueous because nitrates are always soluble. Sodium chloride is aqueous because sodium is a group 1 metal. Silver chloride is insoluble according to the solubility rules, so it forms a precipitate solid. And sodium nitrate remains aqueous because nitrates are soluble. Now let's briefly discuss molecular compounds. Molecular compounds are made from only nonmetals. Many small molecular compounds are gases. For example, carbon dioxide is written as CO2 gas. Sulfur dioxide is SO2 gas. Ammonia is NH3 gas. Hydrogen chloride is HCl gas unless it is dissolved in water. If hydrogen chloride is dissolved in water, we write HCl aqueous because it becomes hydrochloric acid. Water itself is usually written as liquid when pure, H2O liquid, but if ions are dissolved in water, we use aqueous instead. One of the biggest mistakes students make is confusing liquid and aqueous. Liquid means the substance itself is a liquid. Aqueous means the substance has dissolved in water into ions. For example, H2O liquid is pure water. But sodium chloride aqueous means sodium ions and chloride ions are dissolved in water. Another common mistake is assuming every ionic compound is aqueous. That is not true. Some ionic compounds dissolve in water, while others form precipitate solids. That is why the solubility rules are so important. So let's summarize the system. First, determine whether the substance is an element or a compound. If it is an element alone, use its natural state. Remember the diatomic elements in their forms. If you are unsure about the natural form of an element, use a thermodynamic table and look for the form with delta HF and delta GF values equal to 0. If the substance is an ionic compound, use the solubility rules. Soluble ionic compounds are aqueous. Insoluble ionic compounds are solids. And finally, many small molecular compounds are gases. If you can master states of matter, writing chemical equations becomes much easier, predicting reactions becomes easier, and later topics like net ionic equations will make much more sense.